So let us continue from now, and I will attach the first part after the class. Stitch the two videos together. Sorry about this. So we have to think about what are the valence orbitals of our ligands now. So in this case, the decision is easy. Our hydrogen atoms, they only have the 1s orbitals as the valence orbitals. So we would only consider the valence orbitals to be, the 1s orbitals to be the atomic orbitals we would use. Okay, so we have two atomic orbitals that we would combine to form two ligand group orbitals. Okay? So that is the next step. Okay, we have the 1s orbitals that we combine to form two ligand group orbitals. So we know now how many ligand group orbitals we have. So in the next step, we have to determine the symmetry type of these ligand group orbitals. So how do we do this? We do this in two steps. We first determine the reducible representation of these ligand group orbitals, and from that reducible representation, we then determine the irreducible representations. That reducible representation is made of. Remember, a reducible representation is always the sum of two or more irreducible representations. Okay, so now how do we do this? We can do this by a method which is called the orbital swapping method. So we apply the symmetry operations and decide if the symmetry operations swap up the two orbitals or not. When they're getting swapped up, the respective orbitals get a character of 0 in the reducible representation. If they do not get swapped up, then the character is 1. That gives you then all the characters for your reducible representation. So now let us just apply this. So we can start with the identity. So we have to ask ourselves, as we apply the identity operation, do psi1 and psi2 get swapped up? Psi1 stands for the first 1s orbital, psi2 stands for the second 1s orbital. So you probably remember, identity operation never does anything. And for that reason, well, each 1s orbital gets the character 1, and we sum these up. So we have overall 1 plus 1. That gives 2, and that gives the first character in our reducible representation. So then we go from the identity to the C2 operation. So we again determine, as we carry out the C2 operation, do the psi1 and psi2 wave functions get swapped up or not? So in this case, they are getting swapped up. Psi1 moves into position of psi2, and psi2 moves into position of psi1. That means that both orbitals now change the position, and that means that both of the orbitals get the character of 0. So the two zeros add up, well, and that gives overall 0. We have now determined the character, the second character of our reducible representation. So in the next step, we apply the same method to the two mirror planes. So we have the sigma xc mirror plane, which is in the plane of the molecule. So do the orbitals swap their positions? The answer is no, they stay in their position. Therefore, each of them gets the character 1, and these two characters add up to give a character of 2. Last but not least, we look at the second mirror plane. So the second mirror plane stands perpendicular to the molecule. Okay, so do the orbitals get swapped up? In this case, the answer is yes. So psi1 gets moved to the right side, and psi2 gets moved to the left side, gets reflected to the left side. So both of the wave functions get the character 0. These two characters add up, and that gives you the overall character 0. So I've now determined all the characters in the reducible representation, which is 2, 0, 2, 0. So you may wonder what is actually behind the orbital swapping method. So it's again matrices, and I wanted to briefly explain this because the orbital swapping method is just actually a trick how you can actually circumvent matrix calculations. But what's actually behind the orbital swapping method, or why it works, is matrix calculations. So you can again express psi1 and psi2 in a matrix, in a 2 times 1 matrix. And you can again ask, well, with what matrix do I need to multiply this matrix so that the right, final matrix comes out, okay? So now in the case of the identity, in the case of sigma xc, we know that psi1 and psi2 stay in their position. So therefore, the final matrix is equal to the original matrix. Okay, the original matrix has the form psi1, psi2. The final matrix has also the form psi1, psi2. So now, with what matrix do we have to multiply this matrix to get that matrix? Well, that would be again the matrix that would actually represent, in this case, the symmetry operation. Okay, so using the rules for matrix multiplication, you can show that this matrix here, 1, 0, 0, 1, gives you the right product matrix. Okay, so now the characters on the reducible representation are actually nothing but the sum of the characters that you find on the trace of that matrix that represents your symmetry operation. So in this case, it's these two characters, 1 and 1 respectively. So we add that up 1 and 1, and that gives you 2. So now for the other two symmetry operations, the C2 and the sigma YZ, well, the orbitals are getting swapped up. So your final matrix is psi2, psi1. So what is now the matrix representing the symmetry operation? It is this matrix here, 0, 1, 1, 0, because with the multiplication rules for matrices, you can show that when you multiply this matrix with the original matrix, this gives you the final matrix, the correct final matrix. So again, the characters that are the reducible representation are the sum of the characters that are on the trace of the matrix. So in this case, that's this 0 and that 0. So in this case, we have 0 plus 0, well, that gives again 0. Okay, so this is what's behind the orbital swapping method. The orbital swapping method is an easy way to determine the characters on the trace of the matrices that represent the symmetry operations, that convert the wave functions. Okay, so now we have determined the reducible representation. Now we have to determine the irreducible representations that, when added up together, give the reducible representation. Okay, so once we have the irreducible representations, we know the symmetry type, because we know this symmetry type is always associated with a certain reducible representation. So there's a formula in group theory that we can use to determine the irreducible representations from the reducible representation. That's called the reduction formula. And this formula is shown here. Okay. So it says that the number of irreducible representations of a given type, and we mean here a symmetry type. So in C2V, that could be either A1, A2, B1, or B2, is equal to 1 of the order of the point group in C2V, that would be 4, times the number of operations in the class, where by class we always mean a column, times the character of the reducible representation, times the character of the irreducible representation. And we have to determine that product here for all the different symmetry operations and sum up over all the symmetry operations. Okay, so this is what this sum sign here means. Yeah, we determine this product for all symmetry operations. Okay, now let's apply this formula to the problem that we just discussed. So our reduced representation is again listed here. It's 2, 0, 2, 0. So we start with an irreducible representation of a certain type. We can, for instance, just select the first one here in the character table, which is A1. So we now determine the number of irreducible representations that have the symmetry type A1. Okay, so that is equal to 1 of the order of the point group, okay, which is actually 4. So we have 1 4 times the 4 products for the 4 symmetry operations. So now what is that? Well, for the identity, the number of the operations in the class is actually 1, okay, because we have only 1 identity operation. So that explains the first one here in the first product. So then we have to multiply this with the character of the reduced representation. So we look up the character underneath E in the reduced representation, and that is 2. Okay, so that explains this 2 here. Okay, so this is this. And then last but not least, we need to multiply this with the character of the irreducible representation. So that's now the character in the irreducible representation A1 underneath E. So this is this one here, and this is that one here. So now we have to find our first product, 1 times 2 times 1. So now we still have to find the other 3 products. So next we can go to C2. So what is the number of operations in the class? So again, we have only 1 operation, 1 C2 operation to consider in this case. So that explains this one here. So then we have to multiply this with the character of the reduced representation. So we look underneath C2 in the reduced representation. We find that the character is 0. And last but not least, we multiply this by the character of the irreducible representation. Well, that's the character here underneath C2 in the irreducible representation of the type A1. So this is this one. And that is the character over here. Okay. Now we do the same for the first mirror plane, sigma v xc. The number of operations in the class is again 1 because of only 1 reflection operation to consider. We multiply this with the character of the reduced representation. So this is this character here, yeah, underneath sigma xc. So that gives this 2. And last but not least, we need to determine the character of the irreducible representation, which is the one in the row for A1 underneath sigma v, which is this one. We find this character again here. Okay, so now we have to determine the third product. Now, last but not least, let's determine the last product for sigma v prime or sigma yz. So what is the number of operations in the class? Well, that's again just 1. We only have 1 operation to consider. What is the character of the reduced representation? Well, we see it is 0. And what is the character of the irreducible representation? Well, this is this one here underneath sigma v in the row for the irreducible representation A1. So we have 1 times 0 times 1. Okay, now we have found all 4 products, and we just add these 4 products together and divide it by 4. And if we do so, then that gives 1. Okay, because that's 2 plus 0 plus 2 plus 0, that gives 4. And 4 over 4, well, that gives 1. Okay, so now we know that one of the 2 leading group orbitals that we are looking for has the symmetry type A1. Okay, so by applying the reduction formula to the other 3 symmetry types, we can now find also the symmetry type of our second ligand group orbital. All right, So here's the result. If we apply the formula to the symmetry type A2, we would find that the number of irreducible representation of that type is 0. That means no ligand group orbital has the symmetry type A2. So for B1, we find that the number of irreducible representations is 1. That means that our second ligand group orbital that we're looking for has the symmetry type B1. That means, of course, that we are finished now, and the number of irreducible representations of the symmetry type B2 must be 0. But if we applied the reduction formula to the symmetry type B2, this is exactly what we would find. Okay, so now we have determined the symmetry types of our ligand group orbitals. Okay, one has the symmetry type A1, the other one has the symmetry type B1. Okay, and our reducible representation is made of the two irreducible representations. One has symmetry type A1 and the other one B1. All right, so now we can think about intuitive geometric interpretation of that result. Okay, so what does that mean? That the reducible representation is A1 plus B1. Okay, and can we actually show visually that our two ligand group orbitals have that symmetry type? Okay, so now remember in the last class we said, well, there are two ways to combine the two oneness orbitals. Okay, the first way is that the algebraic signs of the two oneness orbitals is the same, and the other way is to have opposite algebraic signs for the two oneness orbitals. So now the first case relates to the symmetry type A1, and the second case relates to the symmetry type B1. We can again very easily show this by applying the symmetry operations to the respective combinations. Okay? So now when we apply the four symmetry operations to this combination, we see there's no change to the respective orbitals. Okay, so the algebraic sign doesn't change no matter which symmetry operation we apply. Okay, so the identity never does anything. When we apply C2, well, the two oneness orbitals get swapped up because they're both the same algebraic sign, this doesn't mean a change. When we apply the two mirror planes, the same. The first mirror plane doesn't swap up the orbitals. The second mirror plane does swap up the orbitals, but because they have the same algebraic sign, again, the resulting wave function doesn't change its algebraic sign. So that relates to characters of 1 in the respective irreducible representation. Okay? And only the irreducible representation of the symmetry type A1 has all 4 characters to be 1. Okay? So now, in this combination here, the situation is different. So when we apply the identity, okay, the wave function, overall wave function, doesn't apply the algebraic sign because the orbitals stay in their position. But now, as we apply the C2 operation, you see the right one moves to the left and the left one moves to the right, but as they do, the algebraic sign of the wave function changes, okay? And that relates to a character of -1 in the respective character table. And therefore, the symmetry must be B-type, okay? So as we apply the sigma xc operation, again, the orbitals do not change their position, therefore the algebraic sign of the overall wave function doesn't change. And the character in the irreducible representation is therefore a +1. But as we apply the second symmetry operation, the second mirror plane, again, the orbitals swap up. And as they do, the algebraic sign of the combination of the orbitals swap up, okay? What was formerly positive is negative, and what was formerly negative was positive. And that relates to a -1 character in the respective irreducible representation, okay? And therefore, it's B1, okay? We have 1 for the identity, -1 for C2, 1 for sigma V XC, and -1 for sigma V prime, okay? So this is how you can understand why one of the ligand group orbitals has a symmetry type of A1, while the other one has a symmetry type of B1. If you calculated the ligand group orbitals quantum mechanically, they would actually really adopt these forms here, as depicted here. Okay, so now we know the symmetry types of our ligand group orbitals. Now we need to go to the next step and determine the symmetry types of the central atom orbitals. Okay, so here's just again the illustration. When we apply here all the 4 symmetry operations, the resulting orbital is the same as the original one. Here, this is only the case when we apply the identity in sigma xc. If we apply C2 and sigma yz, then the sign of the orbital is swap out. All right. So let us move over now to the next step, which is now about the determination of the symmetry types of the central atom orbitals. So now our central atom is the oxygen. We need to know what are the valence orbitals of an oxygen atom. So these are the 2s and the 3 2p. So we have to determine the symmetry types for each of those. Now for the central atom orbitals, fortunately, the procedure is simpler. We can read the symmetry type directly from the character table. Okay, so the 2s orbital has A1 symmetry. Okay, that is because s orbitals always have the totally symmetric symmetry type, okay, which is always the first one in the character table. So therefore the 2s orbital has the symmetry type A1. So now what about the p orbitals? Now you can simply look where the respective mathematical functions are located in the character table and then read the symmetry type from there. So you know that the pz orbital is a linear function of z. You see that the letter z appears in the first irreducible representation with the symmetry type A1. That tells you that the 2pz orbital has the symmetry type A1. So now we can do the same also with the 2px orbital. So you just look where the letter x appears in the character table. You see that it appears in the irreducible representation of symmetry type B1. That means that the 2px orbital has the symmetry type of B1. Last but not least, we also looked at the 2py orbital. And you see that the letter y is in the irreducible representation of the symmetry type B2. Therefore, you know that the 2py orbital, the molecule here is actually wrong, that has to say orbital, has the symmetry type B2. So now you know the symmetry types of your ligand group orbitals. You also know the symmetry types of your central atom orbitals. So now you can combine orbitals of the same symmetry type to form molecular orbitals. So this is now the next step. Okay? We determine which group orbitals and central atom orbitals have the same symmetry type. Okay. So now the orbitals of the same symmetry type must be combined to form MOs. So if an orbital has no partner, then that means that orbital remains non-bonded. So let's apply this step by step to our problem. So we said that the 2s orbital and the 2pz orbital has a symmetry type A1. We also determined that one of the ligand group orbitals has the symmetry type A1. So that means that we can combine these three now to form molecular orbitals. So now the number of molecular orbitals is always the same as the number of the orbitals from which they have been made of. So we combine three, therefore we actually get three molecular orbitals, and they have the same symmetry type A1. We have three molecular orbitals with symmetry type A1. So secondly, we look at the symmetry type A2. You notice we have no central atom orbital. We have also no ligand group orbital of the symmetry type A2. Therefore, naturally, we will also have no molecular orbital of the symmetry type A2. So next we go to symmetry type B1. We see that we have the 2px orbital having that symmetry type, but also the second ligand group orbital having the same symmetry type. Therefore, we can now combine two orbitals to form two molecular orbitals. Okay, last but not least, we have the symmetry type B2 to consider. So we said that the 2py orbital has that symmetry type. Now, do we have also a ligand group orbital of that symmetry type? The answer is no. And that means that the 2py orbital now does not find a bonding partner. Okay? So now remember, in the last class, we determined the same by inspection. Okay? We tried to combine the 2py orbital with the two 1s orbitals. And we saw that no matter how we choose the algebraic sign of the 1s orbitals, the bonding and the anti-bonding interactions always cancel out, meaning that the 2py orbital would remain non-bonding. Now we see you get the same result from the group theoretical analysis using symmetry-adapted linear combination of atomic orbitals, but you get it in a less ambiguous way. You do not need to determine, well, orbital overlaps by inspection, which can be prone of error. Okay? Rather than that, you know that the 2py orbital has a symmetry type B2. There's no ligand group orbital that has that symmetry type. We know, therefore, well, the 2py orbital does not have appropriate symmetry to overlap with the 1s orbitals to form molecular orbital, and therefore it remains non-bonded. Okay, we have now all the information to construct the molecular orbital diagram of water. So how do we do this? Using the results that we have previously obtained. So first of all, as we always do, we write an arrow pointing up, and that arrow indicates our energy. Therefore, we write an E above the respective arrow. Okay, in the next step, we write down the involved atoms, the ligand atoms on the right side, and the oxygen atoms on the left side, as you can see here. So then we write the atomic orbitals according to energy. So the oxygen atom has the 2s and the 2p. Okay, so we know that the 2s has a lower energy than the 2p orbitals. We also know that the 2p orbitals have always the same energy. Therefore, we write them also with the same energy. We can either write the orbitals, well, with 3 lines directly next to each other. We can also write this 3 lines on top of each other with a minimal distance in between them in order to indicate that they have the same energy. So what you also do is that you write the symmetry types of the respective orbitals. So we determined that the 2s orbital has symmetry type A1, and we write that underneath the orbital. So the 2p orbitals had the symmetry type A1, B2, and B1. So we write A1, B2, and B1 underneath the 3 p orbitals. So then, on the right-hand side, we have the 2 ligand group orbitals, LGO1 and LGO2. So we can write LGO1 with somewhat lower energy than LGO2. That is because LGO1, the one with the A1 symmetry type, does not have a node. That is because both 1s orbitals have the same algebraic sign, while the other one with the symmetry type B1 actually has a node because the 2 1s orbitals have the opposite algebraic sign. Yeah. You can, however, and that's still accurate enough, also write them with the same energy. You can also find that in the literature, but if you want to be particularly accurate, write the LGO1 somewhat below the energy of the LGO2. The difference is not large anyway, because there's not a lot of overlap between the 1s orbitals in the hydrogen molecule anyway, so it doesn't matter a lot whether the algebraic signs are the same or different. Okay. Okay, so now you also assign the symmetry types to these 2 ligand group orbitals, which is B1, A1, and B1 respectively. So now you can combine orbitals of the same symmetry type from molecular orbitals. So it doesn't matter with which symmetry type you start, you just have to consider all of them. You can start, for instance, with the symmetry type A1. So you know we have 2 orbitals of that kind here on the left side, we have 1 on the right side, that's overall 3, so we must get 3 molecular orbitals. So when you have 3 molecular orbitals, you can qualitatively estimate, yeah? And we are constructing molecular orbital diagrams here only qualitatively, not quantitatively, meaning that we do not compute the actual energies of the orbitals, we only estimate them, yeah? We can estimate that 1 orbital will be bonding, and that will have low energy, that 1 orbital will be anti-bonding and will have high energy, and that the 3rd orbital will be approximately non-bonding, can be somewhat bonding or anti-bonding also, and has intermediate energy. And you write the orbitals accordingly into a molecular orbital diagram. Okay? So this is the first one, this is the second one, this is the third one. So the bonding one should always be energetically below the atomic orbital that has the lowest energy in the same symmetry type. So it's in this case the 2s, and the anti-bonding one should always be in energy above the energy of the atomic orbital ligand group orbital, which has the highest energy. So in this case, that would be the 2p orbital. So the 3rd orbital, which is the 2a1, which is here approximately in the middle. So now you label these orbitals also according to symmetry type, and by convention, molecular orbitals get lowercase letters, as opposed to atomic orbitals or ligand group orbitals, which get uppercase letters. So the molecular orbital with the lowest energy gets the number 1 or the coefficient 1. The one of intermediate energy gets the coefficient 2, and the one with the highest energy gets the coefficient number 3. All right, so last but not least, we indicate that these molecular orbitals here have been made from atomic orbitals and ligand group orbitals with the same symmetry type by connecting the respective orbitals with dotted lines. Okay? So all 3 orbitals here have an influence from the 2s, because the 2s has the same symmetry type. Okay. Then all three orbitals here have an influence from the 2p orbital, which has the symmetry type A1, as you can see here, here, and here. And all three orbitals here have an influence from the ligand group orbital, which has that symmetry type A1, as you can see from these dotted lines. Okay? Sometimes, when a molecular orbital is very far away in energy from an atomic orbital with the same symmetry type, these dotted lines are not drawn. Okay? You can find this in the literature sometimes also. That just indicates that, well, the interaction or the contribution of that atomic orbital to the molecular orbital is so small it can actually be neglected. But strictly spoken, when two orbitals have the same symmetry type, then there's always some interaction, even though this interaction may be small because the energy differences may be large. Just wanted to mention this because you can find this sometimes in the literature and also sometimes in textbooks. Okay, now we are done with the symmetry type A1. Now let's go to the symmetry type B1. We realize we have one atomic orbital of that symmetry type. We have also one ligand group orbital of the same symmetry type. We would therefore expect two molecular orbitals. Now, when we have two, we would expect that one is bonding and has a lower energy, and one is anti-bonding and has a higher energy. So we would write these orbitals accordingly into the molecular orbital diagram. You see here the bonding one having a lower energy, and the anti-bonding one having a higher energy. We indicate the symmetry types with lowercase letters, in this case B1, and we again number these orbitals by giving them the respective coefficients. This one gets the coefficient 1, and this one gets the coefficient 2, because this one here is lower in energy than this one over there. So again, the bonding one should be energetically below the atomic orbital or ligand group orbital of the lowest energy. So in this case, this would be one of the 2p. The anti-bonding one should be above the atomic orbital or ligand group orbital of the same symmetry type as the highest energy. In this case, it would be LGO2. So we again connect the respective atomic orbitals, ligand group orbitals, molecular orbitals with dotted lines to indicate what molecular orbital has been made from what atomic orbital and what ligand orbital. All right, so now as we construct our qualitative molecular orbital, we cannot unambiguously determine the relative order of the energies of the molecular orbitals in all cases. So for instance, it is not completely certain that basically the 3A1 has a lower energy than the 2B1 based on our qualitative estimates. It is also not entirely certain that this 1A1 has a lower energy than this 1B1, even though in this case you would strongly suspect this because the 1A1 has contribution from energetically very low to S, while the 1B1 has not. It has only contributions from a 2p orbital and a ligand group orbital. Okay, therefore, it is more likely that the 1B1 has a higher energy than the 1A1, but with an exact without an exact calculation, you could not unambiguously prove this. So this is a limitation of the qualitative construction of molecular orbital diagrams. Sometimes the relative order of molecular orbitals can be ambiguous. Okay, so if you have to construct a molecular orbital diagram in an exam, then let's say you had or that the energy of these two, I would not count as a mistake because it's not entirely unambiguous. All right, but of course we can also make some statements with certainty. For instance, that we have 3 orbitals of the symmetry type A1, and one must be bonding, one anti-bonding, and one approximately non-bonding. And they should be written in the molecular orbital diagram also at home. Okay, so now what's left is the electrons. So, oh no, we have still forgotten the B2 symmetry type. So the 2py orbital has the B2 symmetry type. Now we determined that this orbital is non-bonding, and therefore we have to write it accordingly into the molecular orbital diagram. This means that we must write it with the same energy as the 2py orbital into the molecular orbital diagram. Again, we indicate the symmetry type and give it a coefficient. In this case, we have only one orbit of that kind, so we have only one coefficient, which is 1. So now we are really finished with the construction of molecular orbitals. We still fill in the electrons. So now the oxygen atom has 6 valence electrons. So according to energy, 2 of them must be in the 2s orbital, and the remaining 4 must be in the 2p orbitals. And then on the other side, the hydrogens contain 1 electron each. That gives overall 2. So now that gives overall 8 electrons, and we must fill the 8 electrons now according to energy into the molecular orbital diagram. So that means that the 1a1 gets filled, the 1b1 gets filled, the 2a1 gets filled, and the 1b2 also gets filled. Yeah, of course. Then we have 2, 4, 6, 8. Okay, so that makes this orbital here our highest occupied molecular orbital. The 3a1 here would be our lowest unoccupied molecular orbital. So now we can compare the result that we obtained from molecular orbital theory with what simple valence bond theory would tell us about the bonding in the same molecule. Okay, so in the simple valence bond picture, we would have 2 OH single bonds, and we would have 2 electron lone pairs. So according to the simple valence bond picture, we would have 4 bonding electrons. Can we find those also in the molecular orbital diagram? And the answer is yes. Okay, because these 2 bonding molecular orbitals are filled. We have no anti-bonding molecular orbitals being filled, so therefore we can say, yeah, we have overall 4 bonding electrons in our molecule. Now we see, however, that you can get additional information out of your molecular orbital diagram. So in the simple valence bond picture, these 4 electrons here appear all equivalent. Yeah, or the 2 OH bonds appear completely equivalent. You see that the molecular orbital diagram, this is not the case. These 2 electrons have a lower energy than these 2 electrons. So that is not something which would be visible from the simple valence bond picture. So you see here that the molecular orbital diagram gives more information in comparison to the simple valence bond picture. Something similar you see when you look for the 2 electron pairs here in the molecular orbital diagram. So an electron pair is naturally non-bonding. Yeah, and you see here we have 2 approximately non-bonding molecular orbitals. So this is actually exactly non-bonding. So this is our 2py orbital. But also this one, the second 2a1, we said it's approximately non-bonding. Therefore, it would be correct to assign these 4 electrons here to these 2 electron lone pairs. Yes?
So even though, for example, the 2 sigma bonds have different energies? Is it arbitrary which one has which energy?
Yeah, again, we could not unambiguously say that this one has a lower energy than that one. That's correct.
If you actually assign those to the lone pairs, which one would go for which?
No, you could not say this because according to this picture, they again appear equivalent, right? While here you see, well, 2 electrons have a lower energy than the other 2. So again, you can get actually more information out of your molecular orbital diagram in comparison to the simple valence bond function. Okay, so overall you see that your molecular orbital theory gives you a very detailed picture about the covalent bonding in the molecule, but of course that comes at the expense of complexity. It's much simpler to write a water molecule using simple valence bond theory rather than constructing molecular orbital diagrams. Which method you choose depends on, well, how much information do you really need in order to solve a particular problem chemistry. Okay, then let's stop at this point.